let's review the principle of virtual work a little bit. So for general 3D solid and structural problem, we have a principle of virtual work. Fi So left-hand side is the internal virtual work done by stress, and right-hand side is the external virtual work done by external force applied. Okay, and for bar case, this equation can be specialized something like this. P Exx dx equal 0L Q U dx K plus K, let's say F and U 0L, right? So the first equation and second equation looks very similar, right? Only difference is the term. So here for bar, we are using the internal force P instead of stress. Strain, the bar have only one strain component, strain in longitudinal direction, and instead of body force F, we are using Q, distributed force. And here, instead of surface force, we are using the force applied at the each end of the bar, right? And also, for general spring case, this equation, we have equation P E equal F1 U1 plus F2 U2, right? Same thing. For spring case, we don't need to integrate this equation for bar along the beam length. So equation become much simpler. So left hand side become just spring force and stretch. Right hand side, we don't have a distributed force, and this term becomes just like this, right? Very simple. And for general truss system, which has many members, this equation can be modified like this. N Pi EI equal 1 M Fi Ui. The equations looks different, but these are all the principle of virtual work. Okay? So, 정호, are you familiar with maybe this one or this one, right? Maybe this one, or you know this equation. Undergrad school, some you studied already, right? And you use this equation to solve a truss system, right? Okay, then today I like to show you example. Simple, very simple truss system which have only two members. So system is like this. Here we have a vertical bar, okay, and tilted bar here, and hinge connection. So we have a two bar. Let's say this bar is a member 1, member 2. So this is a truly truss structure which consists of two bar, right? And member 1, bar member 1 has a stiffness K1, member 2, K2, and let's see the internal force P1, internal force P2. So P1 and P2 is a tension force. So tension is positive, compression is negative. Usually we are using that kind of convention. And let's say here displacement U1, U2. Of course, then force F1, F2. So at this point can move in two ways, one direction and two directions. So X direction and Y direction, right? And at this point, we can apply two different loads, F1 and F2. Then we can express all the possible displacement and force applied. Right? In the truss structure, force can be applied only on the pin. This is a pin, right? Pin. Not apply on the member. That's the one of our assumption. When we analyze the truss structure, okay. So now I like to solve this problem based on principal virtual work here, the last equation. So given is the shape of this structure, okay, ranks, okay, ranks. So from the ranks we can have a calculate stiffness, right? K1, K2, and geometry is a given. This is 45 degree. And boundary condition, displacement boundary condition is given, and force is given. So F1, F2 is externally applied force. So what we need to do is to calculate U1, U2, right? And P1, P2. Okay, that's unknown. So once we calculate U1, U2, we can calculate P1, P2. So now let's use displacement-based method. The main unknown is U1, U2. We need to calculate. Okay? Okay. So let's calculate two possible displacement pattern. One is like this, 45 degree. First displacement pattern is this one. We have only displacement in x direction. This pin move in x direction. And this will be a deformed shape. Okay? Let's say this is a U1. amount of U1. Okay, this is the first possible displacement pattern. The other one is this one. Displacement in y direction. U2. Okay. Then this is a displacement pattern. So let's consider two possible displacement pattern. Okay. We can we imagine the other possible displacement pattern in this problem? This is all the displacement pattern which is possible. Okay. Okay, so let's consider these two cases. Let's say let's look at this one. In this case, the member one is moving in this way. So let's say stretch one equal, in this case, what's going to be a stretch? Is there stretch or not? For member one, this movement is just like a rigid body rotation. Okay, this is a part of rotation of this member, rotate about this axis. So, because we are considering small displacement assumption, when this bar is rotate about this axis, this point, there is no stretch. Okay? How about stretch of the member 2? I like to calculate the stretch of member 2. This is member 2, right? From here to here, this member will rotate about this. So something like that. Okay? So we can just make a line from here to here, right? Then from here to here will be a stretch. E2. Okay? And initially, this is 45 degree. And if you look at this triangle, 90 degree, and this is 45. So, stretch 2 and U1 has a relation. Okay? So, square root 2 U1. Right? Can you understand? Jong-ho, you understand? Okay. How about the second case? Second case, E1 equal. How about E1? E1 is stretch of this member. Same to U2, right? How about E2? So originally, the length of E1 was like this, and it's stretched. It's exactly same to U2. Stretch of E2 can be also similarly calculated. This point can move to here, so 45 degree. So this is a stretch, E2. 1 square root 2, U2. Right? So here we calculate the stretch when the displacement u1이죠. applied, or when we have a displacement only u1. Here, this stretch, when we have a displacement u2. When we have both displacement, we can also calculate stretch. This is sum of both, right? So E1 equal U2, right? U2. E2 equal square root 2 U1 plus U2. What's this? This is the relationship between stretch and displacement. Okay? This is something like the relation between strain and displacement, right? Same thing in this case. Okay. And here we considered real displacement case. This is real displacement. We can also consider virtual displacement. We can consider this is virtual displacement. This is virtual displacement. We can also calculate the virtual strain, virtual stretch like that. So for virtual case, real, virtual strain E1 equal virtual displacement U2, E2 equal virtual U1 plus delta U2, right? So we are using same displacement for pattern for virtual and real, okay? Okay, and let's consider also relation between force and stretch. P1 equal K1E1. P2 equal K2P2. Right? So now we are ready to use principle of virtual work. Okay? So principle of virtual work this case, P1 and virtual strain, virtual E1 plus P2 E2. Because we have only two members, right? So internal virtual work produced by each member from member 1 from member 2. And external virtual work by F1, virtual display U1 plus F2, U2, right? Okay, now let's use all of this equation. Okay? Here P1 equal K1. So this term become E1 K1 E1 plus E2 K2 E2 plus F1 U1 F2 U2. Right? And then let's use this one. Relation between displacement and stretch, virtual displacement and virtual stretch. Okay, E1 equal U2 and K1. Virtual displacement E1 equal U2 plus E2, 1 square root 2 U1 plus U2 K2 and 1 square root 2 virtual displacement U1 U2. Okay, this is equal F1 U1 F2 U2. So now we have equation here. So this equation should be satisfied for all the possible virtual displacement patterns. In this case, we have only two virtual displacement patterns. So all the possible virtual displacement, so it means this equation should be satisfied regardless of the value of virtual displacement U1 and U2. Okay? So for this equation should be satisfied for any amount of, so this equation should be arbitrary okay, even this value is 1,000, 100, this value is million, billion, this equation should be satisfied. Okay? There is only one way to make this equation is satisfied for arbitrary virtual displacement value. Okay, there is only one way. Okay. So how to do that is very simple. We can rearrange that equation about virtual displacement U1. Then we can have equation 1 over 2 K2 U1 plus U2 minus F1 plus U2 K1 U2 plus 1 over 2 K2 U1 plus U2 2 minus F2 equals 0. So for arbitrary virtual displacement U1, U2, to make this equation 0, so this should be 0, this should be 0. So we have two equations, right? First equation is this one equals 0. Second one is this one equation equals 0. So finally, this is both a linear equation. Finally, we can write down matrix form. In matrix form, 1 over 2, K2, 1 over 2, K2, K1, U1, U2 equal F1, F2. Right? This is final equation. In the final equation, we don't have any virtual displacement. Okay? So this K1 and K2 are given, and F1 and F2 are given. So we can calculate U1, U2. Okay, any question? Don't you understand? Procedure is a little different from what you studied. in undergrad school, right? And I think this is much more clear. Okay, any question? No question? Okay. So I'm sure 100% you should solve the one of the problem using the principal virtual work in your final exam. Okay. So this is very important thing. You know this procedure is a 항등식. You already learned this, right? In high school. Okay, so today let's drive a principal virtual work for beam. So we drive the principal virtual work for bar from the general principal virtual work for 3D solid, right? But principal virtual work for bar is very hard to be derived from the general 3D case. So we need to do some special effort. Okay, let's consider bar. You should remember the bar equation we derived long time ago. This is y-axis, and distributed force Q is applied. Okay, Q is a function of x, x-axis. This length is L. Let's consider this bar. You remember equilibrium equation for bar? Huh? Equilibrium equation for bar was that second order ordinary differential equation m minus q equal 0. This was the equilibrium equation. For beam, sorry, not bar. Okay, so the starting point to drive the principal virtual work for beam is this equilibrium equation. So in this equation, m minus q, this is 0. We are multiplying the virtual displacement V. This is a transpose displacement. Displacement in y direction. Or we can say this is a virtual deflection. V is a arbitrary virtual displacement. Okay. So then this should be 0. This equation should be 0. Right? Here, even I integrate from 0 to L dx, this equation should give us 0 value. Of course, this virtual displacement pattern can be arbitrary, but should be continuous. Okay? And should satisfy the displacement boundary condition. Same. Okay, so that equation have a two part, can be divided by two part. V square m dx minus 0 L q dx equals 0, right? So when we derive principle of virtual work, we use the integration by part, right? So in this case, we should also use integration by part. So for the first term, we can use integration by part. The first term is the same to V m 0 to L minus V x m. This is an integration by part, right? And even more, in this equation, we can use the relation between moment and shear force. So this part become minus V 0L minus dx. You know, from here to here, we know the relation between partial x, partial m equal minus v, right? We know this equation, right? Relation between moment and shear force. Okay, then this equation, I can rewrite this equation. This equation become minus x v m dx. Okay, and minus v 0L minus 0L v q dx equal 0. So here we have three terms. Right? And if I move these two terms into the right-hand side, this big equation can become like this, plus, minus, right? And here, let's look at this term. This term can be substituted by the result of integration by part again. So this term equals same to delta V M 0L minus 0L V M dx. This is your integration by part again. And let's look at this term. What's this? Physically. In Euler beam theory, let's consider this is we are using Euler beam theory. So if I take the derivative of displacement once, we can calculate the slope, which is a rotation. So if I take the derivative of displacement about x twice, then what we can have? So this just become if we take the derivative of the rotation, what we can have? This is curvature. Okay, this is curvature. Let's say this is curvature. So here, like C, this is curvature. So you know the meaning of curvature? What's the curvature, 정호? Curvature. Yeah. For example, let's say we have a curve here. And at this point, curvature is defined by the, at this point here, this part of the curve looks like a circle, right? So using this circle, this part of a circle, we can make a big circle. Then we can calculate the radius r, right? And here also we can make something like that, any point. So if the slope is big, change of slope is big, the radius becomes smaller. So change of slope is small, the radius will be very big, right? And curvature is just inverse of that radius. This R equal in Korean 공률 방정. Okay. Okay. So if I summarize theta equal in Euler beam theory, this is a rotation. Curvature. So if I use the result of integration part by part in this equation, we can finally obtain the equation. Principal virtual work for Euler beam. 0, L. Virtual curvature M dx equal 0, L Q dx plus 0L plus here this is a rotation, right? Theta plus theta M 0L. This is a principle of virtual work for Euler beam. That's the final equation. So here, left-hand side is a internal virtual work. How can we calculate the internal virtual work for Euler beam? Internal moment, okay, and virtual curvature. Okay, so we need to calculate the curvature to calculate the internal virtual work for Euler beam. And right-hand side looks very simple, right? This is external virtual work calculated by distributed force Q, and this is internal virtual work calculated by the end moment and end shear force. Shear force applied each end here and here. So at 0 and at L. So shear force, this is a V1, V0, VL, and M0, ML, something like that. Because this is a one-dimensional structure, and this is something like a surface for that beam. And how we can enforce the boundary condition? Boundary condition can be enforced here by using the virtual displacement, V. For example, if we impose, if you want to solve this case, cantilever case, at here you need to impose the here at here theta equals 0, displacement 0. This can be imposed by virtual displacement and displacement 2. So theta B okay, so I'd like to show you example. Even we have just 5 minutes. Example. Let's consider simply supported beam. Okay, O length L. X-axis start from the left end. And distributed force Q is applied. Q. We can solve this problem very easily, right? Right? But today I like to show you some power of principal virtual work. Principal virtual work can be used to approximate the exact solution. Okay? This is the integral form of equation. This can be used for approximation too. This is a really, really big power. Okay? Very, very strong advantage. Using the weak form, strong form, we can calculate exact solution, right? But if we use the weak form, we can calculate exact solution, and also we can calculate approximation. Okay, so I'm going to show you how to do. First, okay, let's approximate the displacement pattern of this. It looks like this. Okay, this is B, and displacement pattern is A sine L pi x. This is approximation. Okay? We can approximate. And then virtual displacement pattern, we are using same virtual displacement pattern, A sine L pi x. Using this approximation, once we calculate A, that's going to give you approximation. Okay? Then let's use this principal virtual work. Okay? So, because we don't have we don't need to calculate these two terms. In that case, we need to use only this equation, right? We need to solve. We can calculate virtual curvature from this equation. Virtual, so twice, and right? Also, we can calculate M from the EI material law. This is material law. This is relation between moment and curvature, right? And right-hand side is very easily we can calculate. And if I do some calculation, we can calculate the A. And from A, we can calculate the B. Okay, minus pi y 4 EI QL sine L pi x. This is A. Okay. This is an approximate solution we found from using the principal virtual work and exact. B exact equal EI Q X this is exact, and this is approximation. Let's say here approximation. Looks much different, right? Then here, if I calculate approximation at deflection at the center, this will be maximum deflection. if I calculate this become minus 0.1371. And in this case, B exact L over 2 equal let's compare both number. Okay, looks very similar, very small error, right? So here the point is that we can use the principle of virtual work to approximate the solution. So key is the function. If we use very nice function, we can have a very nice result. If we use very bad function, we can have a very bad result, right? So solution of approximation depending on how to assume the displacement pattern. Okay?